Folks, I wanted to take the time to go over question 6 of the week 6 AP exam review. The other parts, if you submit anything, even a blank sheet or scribbles, the AP Classroom will open up the solutions for you to look at. So if you want to see those, just make sure you submit something. If you don't understand their explanations, please shoot me an email and I'll be happy to go over. I wanted to go over question 6 in particular because on every other year, the AP exam has 5 regular FRQs that are supposed to take around 12 minutes apiece. So those would be like the ones that we did in after each unit this year. And then they'll have one that's more in-depth that takes 25 minutes. And that one, they'll go beyond the normal understanding of the curriculum. They'll try and stretch your intuition. So you might see some unfamiliar sort of statistics in there, and that's what this one is. So I'm going to talk you through how to do this one. All right, a large company produces an equal number of brand name light bulbs and generic light bulbs. The director of quality control sets the guidelines that production will be stopped if there is evidence that the proportion of all light bulbs that are defective is greater than 0.1. The director also believes that the proportion of brand name light bulbs that are defective is not equal to the proportion of generic light bulbs that are defective. Therefore, the director wants to estimate the average of the two proportions. To estimate the proportion of brand name light bulbs that are defective, a single random sample of 400 brand name light bulbs is taken, and 44 are found to be defective. Let X represent the number of brand name light bulbs that are defective in a sample of 400, and P sub X represent the proportion of all brand name light bulbs that are defective. It is reasonable to assume that X is a binomial random variable, and one condition for obtaining an interval for P sub X is that the distribution of P hat sub X is approximately normal. So remember what they're talking about here. P hat sub X is the sampling distribution. And it says, is it reasonable to assume that the condition is met? Justify your answer. And so if we want to check normality of a sampling distribution, so of P hat X, we want to use that large counts condition, which is going to be n, our sample size, times P hat, has to be greater than 10, and n times 1 minus P hat, whoops, also needs to be greater than 10. So n being our sample size is 400. So it'll be 400 times my P hat. Well, they said 44 were defective, so my P hat would be 44 out of 400. So if I multiply 400 times 44 out of 400, that's just going to leave me with 44, which is definitely greater than 10. And then n times 1 minus P hat would be 400 times, let's see, the complement of that would be 356 out of 400, which again, that's going to be 356. That's also greater than 10. And so we can say, yes, P hat X is approximately normal. And so that large counts condition justifies that answer. All right, the standard error of P hat X is approximately 0.0156. Show how that value of the standard error is calculated. So standard error, we're going to do square root of P hat times 1 minus P hat over n. And so in our case, remember that P hat was 44 out of 400, and that comes out to 0 0.11. So this comes out to 0.11 times 0.89 over 400, which is 0.0156, which is what we wanted. All right, how many standard errors is the observed p hat x from 0.1? Well, first let's find the absolute difference, which would be 0.11 minus 0.10, which is 0.01. And then we'll divide that by the standard error. So 0.01 divided by 0.0156. And that, if you do that in your calculator, is going to come out to about 0.64 standard errors. All right. So to estimate the proportion of generic light bulbs that are defective, a simple random sample of 400 generic light bulbs is taken and 104 are found to be defective. Let y represent the number of generic light bulbs that are defective in a sample of 400. It is reasonable to assume that y is a binomial random variable and the distribution of p hat y is approximately normal with an approximate standard error of 0.0219. It's also reasonable to assume that x and y are independent. The parameter of interest for the manager of quality control is D, the average proportion of defective light bulbs for the brand name and the generic light bulbs D, defined as D equals Px plus Py divided by 2. So consider D hat the point estimate of D. Calculate D hat from the sample of brand name light bulbs and the sample of generic light bulbs. So great. So D hat is then our proportion of defective brand name light bulbs, 0.11, plus our proportion of defective generic light bulbs. So I'm going to call that p hat y, which is 104 out of 400, which is 0.26. So 0.11 plus 0.26 divided by 2. And our answer is 0.185. All right, calculate S d hat, the standard error of d hat. So then we're going to have the standard error of d hat, because d hat is a transformation and also a combination of functions, right? So d hat, or of binomial random variables. D hat is p hat x plus p hat y over 2. So remember, to find our new standard error, S d hat, we can't just add their independent standard errors. We have to add variance. So I'm going to do the square root of the variance of p hat, which was, let's see, 0.0156. So that's 0.0156 quantity squared, plus they tell us the standard error for p hat y is 0.0219. Plus 0.0219 squared. And then we can't forget that it involves a combination and also a transformation, dividing by 2. So multiplication and division affects measures of center and spread. And so we're just going to divide that answer by 2, and that comes out to 0.0134 when we put that in our calculator. All right. So last section, the average, consider the following hypothesis. Our null hypothesis is that the average proportion of all light bulbs that are defective is 0.10 or 10%. And then our alternative that we're looking for evidence of is that the average is greater than 10%. And so it tells us that a reasonable test statistic for this hypothesis is defined as W. It says, for E, calculate W in your answer to part D, or using your answer to part D. So our W is our D hat value, which was 0.185, So 0.185 minus 0.10 divided by our standard error, which is 0.0134. So throwing that into the calculator, we end up with a test statistic of 6.34. Sorry, I just realized my writing is not showing up. So let me real quick refresh my Wi-Fi. Ah, there it is. All right. So I got a test statistic of 6.34 using the values d hat and the standard error for d hat from the previous part of the problem. Now, F, Chebyshev's inequality states that the proportion of any distribution that lies within k standard errors of the mean. So this is essentially k, because that's the number of standard errors from what we assumed to be the mean, right? Is at least 1 minus 1 over k squared. So if I use my value, so 1 minus 1 over 6.34 quantity squared, I get 0.975. That tells me that 97.5% of d hat values will fall within that value of w. So at the significance level of 0.05, the average proportion of light bulbs that are defective is greater than 10%. So what we want to see is, if we're running a hypothesis test, is this enough information for us to reject the null hypothesis? And the answer is, okay, from that we can say that that means 1 minus 0.975 or 0.025, which is 2.5% of values of d hat. So 2.5% of d hats fall outside of that range. So this is actually the value we want to compare to our significance level. And 0.025 is definitely less than our significance level of 0.05. So our conclusion is that we do have significant evidence that the average proportion of defective light bulbs is greater than 0.10. And that's our conclusion. All right, hope this helps. Email me if you have further questions.